Now coming to part 2 of our discussion, which basically revolves around enriched approximations. We will discuss partitioning of unity, intrinsic enrichment, intrinsic and extrinsic enrichments, the partitioning of unity finite element method, and the generalized finite element method. Now, the partitioning of unity concept is a mathematical concept that is used for making a solution more complete, more closer to the exact solution. Now, a simple generalized format of a partitioning of unity is given by fi of x sigma I equal to 1 to n, fi of x is equal to 1. Or more generally, if we incorporate another function in it, then fi of x into g of x is equal to g of x. So when we use this two finite element method, the interpolation function also satisfy the partition of unity condition, which is sigma I equal to 1 to n, ni of x is equal to 1, and I equal to 1 to n, ni of x, f of x is equal to f of x. When we talk about intrinsic enrichment basically means if we have a basis function p of x, which is a linear function in say x and y, and we have an enrichment function which depends upon f1, f2, f3 and f4, then our basis function, the new basis function that we have, will be a combination of the linear as well as the enrichment functions, wherein you will have 1, x, y, f1, f2, f3, f4. So your displacement function uh of x will become p transpose of x into ax. Ax, as we discussed before, is the unknown degrees of freedom because of enrichment. Additional unknown degrees of freedom because of enrichment. Similarly, in extrinsic enrichment, what we do is, instead of putting these in the function, in the basis function, we add it to that function. Like uh of x is equal to sigma I equal to 1 to n, ni of x ui, ni of x ui plus k equal to 1 to m, pk of x into ak, where ak are the degrees of freedom that are associated with the enriched node. In the case of partitioning of unity finite element method, the extrinsic enrichment is generalized to a partitioning of unity factor fpuk of x into p of x into ak, and for a particular node, say xi, we can write uh of x is equal to ui plus pk of xi into aik. Basically, this is valid only for a particular node. To generalize it, we change this RHS term and we make it pk of x minus pk of xi. In the generalized finite element method, this involves two shape functions. One shape function that is used with the classical definition of finite elements, that is nj of x, and another enriched part of the approximation, which is nj dash of x. Both partitioning of unity finite element method and generalized finite element method, when used in a local manner, are the basis of extended finite element method.